Exoplanet hunters Christopher Watson and Anneliese Mortier explain the long search for a twin Earth capable of sustaining life. On 6 October 1995, at a scientific meeting in Florence, Italy, two Swiss astronomers made an announcement that would transform our understanding of the universe beyond our solar system. Michel Mayor and his PhD student Didier Queloz, working at the University of Geneva, announced they had detected a planet orbiting a star other than the Sun. The star in question, 51 Pegasi, lies about 50 light-years away in the constellation Pegasus. Its companion, christened 51 Pegasi b, was unlike anything written in textbooks about how we thought planets might look. This was a gas giant with a mass of at least half that of Jupiter that circled its star in just over 4 days. It was so close to the star, 1/20th of Earth's distance from the Sun, well inside Mercury's orbit, that the planet's atmosphere would be like a furnace, with temperatures topping 1000 C, 1830. The instrument behind the discovery was LED, a spectrograph that had been installed 2 years earlier at the Haute-Provence Observatory in southern France. Designed by a Franco-Swiss team, LED split starlight into a spectrum of different colors, revealing a rainbow etched with fine, dark lines. These lines can be thought of as a stellar barcode, providing details on the chemistry of other stars. What Mayor and Queloz spotted was 51. Pegasi's barcode sliding rhythmically back and forth in this spectrum every 423 days, a telltale signal that the star was being wobbled by the gravitational tug of an otherwise unseen companion amid the glare of the star. After painstakingly ruling out other explanations, the astronomers finally decided that the variations were due to a gas giant in a close-in orbit around this sun-like star. The front page of the Nature journal in which their paper was published carried the headline, "A Planet in Pegasus?" The discovery baffled scientists, and the question mark on Nature's front cover reflected initial skepticism. Here was a purported giant planet next to its star, but there was no known mechanism for forming a world like this in such a fiery environment. While the signal was confirmed by other teams within weeks, reservations about the cause of the signal remained for almost 3 years before being finally ruled out. Not only did 51 Pegasi b become the first planet discovered orbiting a solar-like star outside our solar system, but it also represented an entirely new type of planet. The term hot Jupiter was later coined to describe such planets. The discovery was the crack in the door that, once opened, resulted in a flood. In the 30 years since, more than 6,000 exoplanets, the term for planets outside our solar system, and candidates for what might be exoplanets have been catalogued. Their variety is staggering, not just hot, but ultra-hot Jupiters with orbits of less than a day. Worlds that orbit not one but 2 stars, like Tatooine from Star Wars. Strange super-puff gas giants larger than Jupiter but with a fraction of the mass. Chains of small rocky planets all piled up in tight orbits. The discovery of 51 Peg b triggered a revolution and, in 2019, landed Mayor and Queloz a Nobel Prize. We can now infer that most stars have planetary systems, and yet, of the thousands of exoplanets found, we have yet to find a planetary system that resembles our own. The quest to find an Earth twin, a planet that resembles Earth in size, mass, and temperature, continues to drive modern-day explorers like us to search for more undiscovered exoplanets. Our expeditions may not take us on death-defying voyages and treks like the past legendary explorers of Earth, but we do get to visit beautiful, mountaintop observatories often located in remote areas around the world. We are members of an international consortium of planet hunters that built, operate, and maintain the Harpsen spectrograph, mounted on the Telescopio Nazionale de Galileo on the beautiful Canary Island of La Palma. This sophisticated instrument allows us to rudely interrupt the journey of starlight which may have been traveling unimpeded at speeds of 670 million mph, 1.08 billion km/h, for decades or even millennia. Each new signal has the potential to bring us closer to understanding how common planetary systems like our own may or may not be. In the background lies the possibility that one day, we may finally detect another planet like Earth. The origins of exoplanet study. Up until the mid-1990s, our solar system was the only set of planets humanity ever knew. Every theory about how planets formed and evolved stemmed from these 9, incredibly closely spaced data points, which went down to 8 when Pluto was demoted in 2006, after the International Astronomical Union agreed a new definition of a planet. All of these planets revolve around just one star out of the estimated roughly 100 billion stars in our galaxy, the Milky Way. The fact there are probably at least 100 billion galaxies in the universe further exposes our ignorance. It's a bit like aliens trying to ascertain human nature and behavior by studying students living together in one house. But it didn't stop some of the greatest minds throughout history from speculating on what lay beyond. The great philosopher Epicurus, 341–270 BC, wrote in a letter to Herodotus, "There is an infinite number of worlds, some like this world, others unlike it." This was not based on any astronomical observation, but on his atomist theory of philosophy. If the universe was made up of an infinite number of atoms, then, he opined, it was impossible not to have other planets. He also clearly understood what this might mean in terms of the potential for life developing elsewhere. We must not suppose that the worlds have necessarily one and the same shape. In one sort of world there might be contained the seeds out of which animals and plants arise and all the rest of the things we see, whereas in another sort of world they could not possibly exist. In contrast, at roughly the same time, fellow Greek philosopher Aristotle, 384–322 BC, was proposing his geocentric model of the universe, which had the Earth immobile at its center with the moon, sun, and known planets orbiting around us. In essence, the solar system as Aristotle conceived it was the entire universe. In On the Heavens, 350 BC, he argued, "It follows that there cannot be more worlds than one." Such thinking that planets were rare in the universe persisted for 2,000 years. Sir James Jeans, one of the world's top mathematicians and an influential physicist and astronomer in the early 20th century, advanced his tidal hypothesis of planet formation in 1916. According to this theory, planets were formed when two stars pass so closely that the encounter pulls streams of gas off the stars into space, which later condense into planets. The rareness of such close cosmic encounters in the vast emptiness of space led Jeans to believe that planets must be rare, or indeed, as was reported in his obituary, that the solar system might even be unique in the universe. But by then, understanding of the scale of the universe was slowly changing. In the Great Debate of 1920, held at the Smithsonian Museum of Natural History in Washington, D.C., American astronomers Harlow Shapley and Haber Kuritz clashed over whether the Milky Way was the entire universe or just one of many galaxies. The evidence began to point to the latter, as Curtis had argued for. This realization, that the universe contained not just billions of stars, but billions of galaxies, each containing billions of stars, began to affect even the most pessimistic predictors of planetary prevalence. In the 1940s, two things caused the scientific consensus to pivot dramatically. First, Jeans's tidal hypothesis did not stand up to scientific scrutiny. The leading theories now had planet formation as a natural byproduct of star formation itself, opening up the potential for all stars to host planets. Then in 1943, claims emerged of planets orbiting the stars 70 Ophiuchus and 61 Cygni C, two relatively nearby star systems visible to the naked eye. Both were later shown to be false positives, most likely due to uncertainties in the telescopic observations that were possible at the time. But nonetheless, it greatly influenced planetary thinking. Suddenly, it was considered a genuine scientific possibility that there were billions of planets in the Milky Way. For us, nothing highlights this change in mindset more than an article written for the Scientific American in July 1943 by the influential American astronomer Henry Norris Russell. Whereas 2 decades earlier, Russell had predicted that planets should be infrequent among the stars, now the title of his article was Anthropocentrism's Demise. Its stand first read, "New discoveries lead to the probability that there are thousands of inhabited planets in our galaxy." Strikingly, Russell was not merely making a prediction about any old planets, but inhabited ones. The burning question was, where were they? It would take another half-century to begin finding out how to detect an exoplanet when we observe myriad stars through La Palma's Italian-built Galileo telescope using our HARPS N spectrograph. It is amazing to consider how far we have come since Mayer and Queloz announced their discovery of 51 Pegasi b in 1995. These days, we can effectively measure the masses of not just Jupiter-like planets, but even small planets thousands of light-years away. As part of the HARPS N collaboration, we have had a front-row seat since 2012 in the science of small exoplanets. Another milestone in this story came 4 years after the 51 Pegasi b discovery, when a Canadian PhD student at Harvard University, David Charbonneau, detected the transit of a known exoplanet. Another hot Jupiter, known as HD 209458b, also located in the Pegasus constellation about 150 light-years from Earth. Transit describes a planet passing in front of its star, from the perspective of the observer, momentarily making the star appear dimmer. As well as detecting exoplanets, the transit technique enables us to measure the radius of the planet by taking many brightness measurements of a star, then waiting for it to dim due to the passing planet. The extent of blocked starlight depends on the radius of the planet. For example, Jupiter would make the Sun only 1% dimmer to alien observers, while for Earth, the effect would be 100 times weaker. In all, 4 times more exoplanets have now been discovered using this transit technique compared with the barcode technique, known as radial velocity, that the Swiss astronomers used to spot the first exoplanet 30 years ago. It is a technique that is still widely used today, including by us, as it can not only find a planet but also measure its mass. A planet orbiting a star exerts a gravitational pull which causes that star to wobble periodically back and forth, meaning it will periodically change its velocity with respect to observers on Earth. With the radial velocity technique, we take repeated measurements of the velocity of a star, looking to find a stable periodic wobble that indicates the presence of a planet. These velocity changes are, however, extremely small. To put it in perspective, the Earth makes the Sun change its velocity by a mere 9 centimeters, 3.5 in, per second, slower than a tortoise. In order to find planets with the radial velocity technique, we thus need to measure these small velocity changes for stars that are many, many trillions of miles away from us. The state-of-the-art instruments we use are truly an engineering feat. The latest spectrographs, such as HARPS N and Espresso, can accurately measure velocity shifts of the order of tenths of centimeters per second, although still not sensitive enough to detect a true Earth twin. But whereas this radial velocity technique is, for now, limited to ground-based observatories and can only observe one star at the time, the transit technique can be employed in space telescopes such as the French Corot 2006-14 and NASA's Kepler 2009-18 and TESS 2018-present missions. Between them, space telescopes have detected thousands of exoplanets in all their diversity, taking advantage of the fact we can measure stellar brightness more easily from space and for many stars at the same time. Despite the differences in detection success rate, both techniques continue to be developed. Applying both can give the radius and mass of a planet, opening up many more avenues for studying its composition. To estimate possible compositions of our discovered exoplanets, we start by making the simplified assumption that small planets are, like Earth, made up of a heavy iron-rich core, a lighter rocky mantle, some surface water, and a small atmosphere. Using our measurements of mass and radius, we can now model the different possible compositional layers and their respective thickness. This is still very much a work in progress, but the universe is spoiling us with a wide variety of different planets. We've seen evidence of rocky worlds being torn apart and strange planetary arrangements that hint at past collisions. Planets have been found across our galaxy, from Sweeps 11b in its central regions, at nearly 28,000 light-years away, one of the most distant ever discovered, to those orbiting our nearest stellar neighbor, Proxima Centauri, which is only 4.2 light-years away. Searching for another Earth. In early July 2013, I, Christopher Watson, was flying out to La Palma for my first go with our recently commissioned HARPS-N spectrograph. Keen not to mess up, my laptop was awash with spreadsheets, charts, manuals, slides, and other notes. Included was a 3-page document I had just been sent entitled, Special Instructions for 2, Target of Opportunity. The first paragraph stated, "The Executive Board has decided that we should give highest priority to this object." The object in question was a planetary candidate thought to be orbiting Kepler-78, a star a little cooler and smaller than our Sun. Located about 125 light-years away in the direction of the constellation Cygnus. A few lines further down, I read, July 4-8 run. Chris Watson, with a list of 10 times to observe Kepler-78 twice per night, each time separated by a very specific 4 hours and 15 minutes. Returning to these notes while writing this article, I realized that the name listed above mine was Didier Queloz's. He hadn't been awarded his Nobel Prize yet, though the planetary candidate had been identified by the Kepler Space Telescope, which was tasked with searching a portion of the Milky Way to look for exoplanets as small as the Earth. In this case, it had identified a transiting planet candidate with an estimated radius of 1.16 plus 0.19 Earth radii. An exoplanet not that much larger than Earth had potentially been spotted. I was in La Palma to use the radial velocity technique to attempt to measure its mass, which, combined with the radius from Kepler, would allow the density and possible composition of the planet candidate to be constrained. Looking at my notes from the time, I had written, want 10% error on mass, to get a good enough bulk density to distinguish between Earth-like, iron-concentrated mercury, or water. In all, I took 10 out of our team's total of 81 exposures of Kepler-78 over the course of an observing campaign that lasted 97 days from start to finish. During that time, we became aware of a U.S.-led team also looking for the potential planet. In true scientific spirit, an agreement was made to submit our independent findings at the same time and simultaneously reveal the results to one another. On the specified date, like a prisoner swap, the two independent teams exchanged results, which agreed. We had, within the uncertainties of our data, reached the same conclusions about the planet's mass. The planet's most likely mass came out as 1.86 that of Earth. At the time, this made Kepler-78b the smallest extrasolar planet with an accurately measured mass. The density was almost identical to that of Earth's, but that is where the similarities to our planet ended. Kepler-78b has a year which lasts only 8.5 hours. This is why my instructions were to observe it every 4 hours and 15 minutes, the times when the planet was at opposite sides of its orbit, and hence when the difference in the induced wobble of the star would be at its greatest. We measured the star wobbling back and forth at about 2 mem-hours, 6.6 per second, no more than a slow jog. Kepler-78b's short orbit meant its extreme temperature would cause all rock on the planet to melt. It may have been the most Earth-like planet found at the time in terms of its size and density, but otherwise, this hellish lava world was at the very extremes of our known planetary population. In 2016, the Kepler Space Telescope made another landmark discovery, a system with at least 5 transiting planets around a sun-like star. HIP 41378 in the Cancer constellation. What made it particularly exciting was the location of these planets. Where most transiting planets we have spotted are closer to their star than Mercury is to the Sun, due to our detection capabilities. This system has at least 3 planets beyond the orbital radius of Venus. Having decided to use our HARPS-N spectrograph to measure the masses of all 5 transiting planets, it became clear after more than a year of observing that one instrument would not be enough to analyze this challenging mix of signals. Other international teams came to the same conclusion, and, rather than compete, we decided to come together in a global collaboration that holds strong to this day. With hundreds of radial velocities gathered over many years, We now have firm masses and radii for most of the planets in the system. But studying them is a game of patience. With planets much further away from their host star, it takes much longer before there is a new transit event or the periodic wobble can be fully observed. We thus need to wait multiple years and gather lots of data to gain insight in this system. But the rewards are obvious. This is the first system that starts resembling our solar system. While the planets are a bit larger and more massive than our rocky planets, their distances are very similar, helping us understand how planetary systems form in the universe. The Holy Grail for exoplanet explorers. After 3 decades of observing, a wealth of different planets have emerged. We started with the hot Jupiters, large gas giants close to their star that are among the easiest planets to find due to both deeper transits and larger radial velocity signals. But while the first tens of discovered exoplanets were all hot Jupiters, we now know these planets are actually very rare. With instrumentation getting better and observations piling up, we have since found a whole new class of planets with sizes and masses between those of Earth and Neptune. But despite our knowledge of thousands of planets beyond the solar system, we still have not found systems truly resembling the solar system, nor planets truly resembling Earth. It is tempting to conclude this means we are a unique planet in a unique system. While this still could be true, it is unlikely. The more reasonable explanation is that for all our stellar technology, our capabilities of detecting such Earth-like planets are still fairly limited in a universe so mind-bogglingly vast. The Holy Grail for many exoplanet explorers, including us, remains to find this true Earth twin, a planet with a similar mass and radius as Earth's, orbiting a star similar to the Sun at a distance similar to how far we are from the Sun. While the universe is rich in diversity and holds many planets unlike our own, discovering a true Earth twin would be the best place to start looking for life as we know it. Currently, the radial velocity method, as used to find the very first exoplanet, remains by far the best-placed method to find it. 30 years on from that Nobel-winning discovery, pioneering planetary explorer, Didier Queloz is taking charge of the very first dedicated radial velocity campaign to go in search of an Earth-like planet. A major international collaboration is building a dedicated instrument, HARPS-3, to be installed later this year at the Isaac Newton Telescope on La Palma. Given its capabilities, we believe a decade of data should be enough to finally discover our first Earth twin, unless we are unique after all.